So the plan for today's session is, I think, as usual, I start by a quick revision, and then I have a couple of examples to solve. And at the end, if you have any questions regarding the homework or anything else, we'll look at that. So what you have been discussing in the lectures now, and I think this part of the course is very, very interesting and very important at the same time. You will need those tools a lot in the future, and they're like building blocks for many other topics to come, like a lot of signal processing, filter design, and many other topics rely on those transformations, like Fourier transform, Laplace transform, Z transform, and so on. So it's so important to understand those topics. So so far in the course, or not so far, I mean before talking about Fourier transform, we were dealing with signals and systems in time domain. And as you have seen, dealing with signals in time domain is not that easy. The main issue is you need to do convolutions, which is not which is not that easy. And also sometimes to analyze a system in time domain, it's not straightforward. I mean, to tell if a system is all of the properties that we have studied, like stability, linearity, time invariance, and so on. Sometimes doing those in frequency domain is easier. So to move to frequency domain, at the beginning, we were asking ourselves, is it possible to to um, to represent those signals in terms of simpler signals? Like, let's say if we have a signal xt, can we represent it as a combination or a linear combination of simpler signals, signals that we can deal with easily, such as sinusoidals, sines and cosines? And we were, or you were interested in writing a signal in this way. Let's say summation k from minus infinity, or something is. What's going on? Just 1 second. Okay, so k equals minus infinity to plus infinity of some weight times some simpler signals, like 5k. So ak will be just some constant, some weight, and then those signals should be easy to deal with. And before talking about those 5k, let's just look at this form. If we have a signal written in this form, then if we apply it to an LTI system, let's say we have an LTI system, linear time invariant system, what the output of this one will be? Can you tell? Can you guess, or what will be the output for if the input was this signal? Since the system is linear and time invariant, and the input is just a summation of scaled other signals, then the output will be also a combination k equals minus infinity to plus infinity. Ak will remain the same because it's a constant. And then we will have, let's say, 5 prime k, which is 5 prime k is the output when 5k is the input. So the output will be also a linear combination of those outputs corresponding to those inputs. That's why this form is easy, and we are looking to write signals in this form because the outputs will be directly similar to the input, just a combination scaled. And then again, we said that those signals need to be simple, so we can take the output for those individual signals, and then we construct this combination and we get the output for any signal if we can write any signal in this form. In the lecture, you have found that, or you have proven that those signal will take the form of exponentials. 5kt is some sort of exponential st, and s, something is wrong with my and st is a complex number, s is complex. Let's say s is written like alpha plus j omega. Alpha is real, omega is real. And do you remember the eigenfunctions or eigenvalues of linear time invariant systems? Those exponentials are eigenfunctions of linear time invariant systems, which means that if I have an LTI system and I use this exponential as an input, what will be the output of this system? It will be some constant multiplied by the same signal. The same signal scaled by some constant. Okay. And you have called this constant Laplace transform. Or this is Laplace transform. And in the special case when S is purely imaginary, this becomes a j omega, because S is just j omega, purely imaginary. And if we use this as an input to the LTI system, the output will be some constant times exponential j omega t. Oh, here we have t, j omega t. And we call this the Fourier transform. Those are for continuous time signals, and we have similar transforms for discrete time signals. Uh, for the discrete time, this becomes Z transform. And the special case of the Z transform, when Z is purely imaginary, we get the discrete time Fourier transform. It's for dt. This is when Z is imaginary. Okay. So the most important thing to keep in mind is that those functions that satisfy this property, when we use them as an input to an LTI, we get the same function multiplied by some constant, are called eigenfunctions of the of the LTI system. Eigenfunctions of the LTI system. So now we know that those 5kt will take the form of exponential. In case of Fourier transform, which is our focus for now, not the Laplace transform, they'll take this form, exponential j omega t. And we will write our signal. Any signal will be written, any periodic signal will be written this way, k equals minus infinity to plus infinity. Some constant times those eigenfunctions, j omega t. Now, if we apply this to an LTI system, the output will be, we know that the system is linear and time invariant. Linear and time invariant. So this linear combination will be also a linear, the output will be also a linear combination. A linear combination with the same constants, and the output for those signals will be, this will be omega k. I don't know what's happening. So the output for those signals will be, as we have seen here, will be some constant times the same signal, because they are eigenfunctions of the LTI system. So let's call this constant lambda k, and then the same function. And you can see how by writing the signal in this form makes it easy to find the output for those signals, because the output of this eigenfunction is the same, just scaled by some constant, and then a linear combination. Let's let's first review the period of a signal again before we continue, because you will use this also in the Fourier when you'll try to find the Fourier series coefficients. So the fundamental period of a signal xt is the smallest t0 in which xt equals xt plus t0 for all t. And then we'll have a fundamental frequency corresponding to this period, which is f0, defined as 1 divided by t0. And if t0 is given in terms of seconds, then the frequency will be in terms of hertz. We can also define the frequency in terms of radians per seconds by using omega 0 equals 2 pi f0. This is in radians per second. And now if we look at those eigenfunctions, we are writing them as exponential j omega kt. So phi kt is exponential j omega kt. And omega k is just omega k is k times omega naught, omega 0. Those frequencies are just multiples of the fundamental frequency. And that's why those functions are called harmonics of the fundamental frequency. It's just multiples of the fundamental frequency. So that's why we say also we are writing xt in terms of its harmonics. So summation minus infinity to plus infinity k ak exponential j. I write it now k omega 0 t. So we are doing a summation over all of these harmonics, and then we scale each harmonic by a different constant, and this constant is given by 1 divided by the fundamental period of the signal, and we do the integration over one period. Doesn't matter where we start and where we end, but we should do the integration over one period of the signal. xt exponential minus j k omega 0 t dt. And we'll use those two equations in the following examples. This one is called the synthesis equation, because we synthesize xt in terms of those harmonics and those scales or scaling constants. And this equation is the analysis. We are analyzing this xt into its harmonic content or frequency content of this signal.